should be streaming. Yep, we are. We are streaming. All right, some housekeeping. We got the exams. Exams are all graded. I posted the grades, so hopefully you saw them. I had to get the key. I don't remember if I did the key or not. Let's check. No, I didn't. I didn't post exam 3 key, the application part of it, but I did do part 1. Part 1 key was posted outside my office, so I think most of you did fairly well on it, at least the application part. We'll get those at the end of class. If you're not here, you can pick it up in lab. Just I'll have to remember to bring them. All right, so our final exams next week. Final exams next week. I'll make the take-home part. That is the application part. That'll go live. My plan is to make it go live on Friday after our class, so that way you can work on it over the weekend. Maybe ease a little bit of stress that you may have during finals week. That'll be due on Wednesday. That is when our final is. So I think our final is scheduled from 10:30 to 12:30. So I'll make it due by like 1 o'clock. So if you are having issues with knitting, you can come in, do the closed book part, and then I can help you get it knitted properly and get it uploaded. All right. The take-home part is going to be a little bit longer, but still it's 2-part exam. Part 1 might take an hour or so total. Well, it's comprehensive. It's comprehensive. All right. I think it's going. Whoops. All right. So other things. We have quiz that I posted, Welch's ANOVA. So, oh darn it, I didn't post it. Christmas lights. You can't take it yet. Don't take it. But Welch's ANOVA, 3 attempts to kind of demonstrate that you can work through Welch's ANOVA and answer questions with the homework. I've also posted ANOVA violating assumptions, and then I have exam prep 1 and 2 that are posted. I posted them as both like a Word document, ODT, a text document, and a PDF. And what you'll see is that this exam 1 is really about like doing some of the tests that we were doing, answering questions. You can use this as kind of like a guide as to what you can expect on application on the application portion. This could also be on the closed book portion. Since we did have some of the probability and like the Bayesian stuff, you test positive, what's the chance you actually have it, and standard probability stuff. And also I could ask, I could set up questions and say, here's the question, what types of tests could we use to answer it? So that's also fair game on that. So that's final exam prep number 1. Final exam prep number 2 is more like general knowledge. If you can go through this and you know these answers and can just rattle off the answers, I think you're going to probably do okay on the final exam. But you can use this as kind of like a study guide, kind of help you answer. And if you don't know the answer, then it gets you into the notes to try to find it, to try to make a study guide for you. So final exam prep 1, final exam prep 2. And then this violating assumptions. The violating assumptions, you can work on it. I think I can put the due date maybe on Friday. So that way we can answer questions during the week as we go through this. Questions? Yep.
What was it? File located?
Which one? It's all put under the homework. Yeah, all under homework. It's all.
file, or is it just or,
Which one?
so there's like two things.
Yep.
But like the first one, when I put it, what is your
I see that opens up for me. Sure. Yeah, for me it automatically downloads. So when I click on it, it automatically downloads for me. So maybe you have to right click and download it. But those are like the Word documents. If you want to open it up and kind of write your answers or your study guide in Word or Google Docs or whatever, it'll work. That's why I did that. Others would prefer a PDF and then take notes on a tablet. All right, so we are almost done with the material, and that's why I've posted all that stuff so we can work through it. We do have one more quiz, probably two more quizzes that I'll have this week. One of them covers the Kruskal-Wallace test, similar to this Welch's ANOVA that we were doing, and then also with permutational tests, just to kind of get you to do this, to come up with some of these. Demonstrate that you can actually do it in like a quiz-like setting. All right, so we're talking about violations of the ANOVA. We have normality within each group, that's a requirement. Equal variances across the groups, that's a requirement. And then data are random and independent. But we don't worry about that one because we design our experiment appropriately. All right, so we're working with oaks and we were doing flowers. We still have turkey data set to work on. So we have flower data set. We basically violated normality. That's what we violated. And we saw it when we did QQ plots. So our options when we violate normality, but we have equal variances, is to run an ANOVA as usual. We're robust to that violation. That's a possibility. Works just fine. We could run a Kruskal-Wallace test. That's a non-parametric test of the median. So it's basically a non-parametric ANOVA. It's an ANOVA of the ranks, is what it is. If we're skewed in the same direction and skewed in the same magnitude, Kruskal-Wallace could work, but that's a test of the medians. All right, that's a test of the medians. If, however, we're skewed in opposite directions, or if there's some that are slightly skewed and some that are really skewed, we probably don't want to run Kruskal-Wallace test. We can still try ANOVA as usual, but our last option is to do this permutational ANOVA. So we ran a regular ANOVA first. We got a significant p-value. All right, and then we went ahead and ran a 2 keys post hoc test just to demonstrate that it can work. R will report answers. But we know that that's not correct because 2 keys does require normality within groups, and we're not as robust to those violations. So while we ran 2 keys to look at this pattern, it's really not the correct way to do it because 2 keys is not robust to the violations. Then we tried Kruskal-Wallace test. With Kruskal-Wallace, we still saw significant effective groups. But once we go the median route, we can't then default back to testing means. We're testing medians. So our options for the Kruskal-Wallace is to do pairwise Kruskal-Wallace test. All right, where we can do, where did it all go? Oh, here it is. So there's this equivalent pairwise.wilcox.test where we do p.adjust method equals home. All right, just like our pairwise.t.test where we set pool.st equals false to do a pairwise Welch's really easily. All right, we get this grid, this matrix of comparisons, or we can manually make subsets where our subsets have 2 groups and 2 groups only. And then from these subsets, we run our Kruskal.test on it. And we get a p-values, and we save all of the p-values. So then when we run method equals home, or p.adjust with method equals home, we get the exact same p-values that we obtained from our Kruskal Wallace or pairwise.wilcox.test. So I copied and pasted the output of that pairwise.wilcox.test here. Pairwise.wilcox.test output, just to demonstrate that we obtained the same p-values manually when we made our own subsets and used p.adjust as if we used pairwise.wilcox.test. We would see the exact same thing if we did pairwise.t.test and the bar I equals f, and run a series of pairwise Welch's t-tests and adjusting our p-values. So either way works, but we introduced the long way. So here's our test again. We introduced this long way because we needed to learn how to make these subsets, because that leads to our third option. And that's what we're going to talk about today. Oops. I guess I can't use that. Option 3, permutational ANOVA. So this is our last option. So with all of our randomization tests, and we have randomization tests for basically any type of test that we want to run. They are great because they are basically considered distribution free. They are distribution free, which means, I'm going to say, basically means that we don't really have the assumptions. But in this sense of distribution free, it means that the test statistic does not follow a specific probability distribution if a certain set of assumptions are met. In reality, this means that we have only one assumption of this test. And that assumption is that data are random and independent. All right, so we don't have to make assumptions that the data are normally distributed. We don't have to make assumptions that variances are equal. We're not making any assumption that our data follows certain distributions. All right, it's kind of part of what this distribution free means. But we do assume that our data are random and independent because our randomization methods is going to shuffle our data and eliminate any pattern or dependence in our data. All right, so if we were doing, let's say, heart rates before and after exercise, we have, average heart rate before exercise, average heart rate after exercise. We're interested in the effect. Does it cause an increase or a decrease? Or does exercise cause an increase, decrease, or no change in our heart rate? We have dependence there because if you have a naturally high heart rate before exercise, it's going to be even higher after heart rate or after exercise. If we were to assume that our data are random and independent and we shuffle their data, we're going to get a very different null distribution. It's going to test a very different types of question than if we were just asking, does exercise cause an increase in heart rate? All right, because the randomization kind of ignores or assumes that our data are actually random and independent. So that's only one assumption. That's all we have for this test. All right. We use randomization tests when we violate assumptions. It's when we can use it. And it doesn't matter which one we use. It doesn't matter which assumption we violated or how many assumptions we violated. Second is when we have small sample sizes within groups. And this is really where you have, let's say, call it one or a few groups that have, let's say, 20, 30 samples, but then you have that one group that only has 5. So the effective sample size is pretty large. Or can be pretty large when trying to detect differences in like means and medians and stuff. And our third we want to maintain consistency in analyses. And I'll just explain that as saying you're doing a research paper or a research project and you have several tests that you're running, and if one of them requires you to run a randomization test because you violate assumptions, maybe it's just easier to run randomization tests for all of your tests. And then you can just state in your methods, hey, I ran permutational ANOVA on all of these tests, instead of saying I'm going to check the assumptions first and run ANOVA in this case, and if I violate it, then I'll run a permutational ANOVA. It's just consistency, maybe ease of explanation, and so forth. All right. What is a randomization test doing? In essence, we are generating the null distribution using our own data. So I'm going to go up here and just add like a subheading. Because we're going to get to this applies to permutational ANOVA, but I'm providing the background for any type of randomization test. Okay, so what does a randomization test do? We're going to generate the null distribution using our own data. What's a null distribution?
The collection of all the data that's been randomized.
You're close. So it's all possible combinations of our test statistic. And it kind of depends on how we phrase it. But the null distribution is all the possible iterations of our data that we can get. All right? And we have what we actually observed, and then we have the collection, all that's out there, assuming that all of our data comes from one population. All right? The t distribution. That was the null distribution used for a 1-sample t-test and a 2-sample t-test. The F statistic, the F distribution, that's our null distribution of ANOVA and Levine's or Brown-Forsythe test. The chi-square distribution, that's a test distribution for our Fligner-Killeen and for a chi-square test, as well as a g-test. But we won't get to those. All right, so those statistics, those distributions all assumed or made certain assumptions about our data. We're not going to do that. We're going to generate our own distribution using our own data. All right. We then compare our observed data to the null distribution to determine if our data what would be a good phrase for that? Could be randomly drawn from the null distribution. So you'll have to recall the definition of a p-value, right? It's a probability of getting data as extreme or more extreme, which by chance alone, than what we actually observed. So probability of getting data as extreme or more extreme than what we observed if our null hypothesis was true, and our null hypothesis was always that we're in the same group. There's no difference, right? No difference in the same group, whatever. All right, so that's kind of what we're doing. we generate our null distribution, and then what we're going to do is look at our observed data and say, well, how likely is it to get our data or something more extreme just by random chance alone? And the p-value then represents the area under the curve of our null distribution. So this could be an example. We'll get to it. We'll get to it. All right. So the general process, and for now we're going to talk about permutational ANOVA, because then we could extend this process to everything, to any type of randomization test. So our question with the permutational ANOVA is, are the means equal across the groups? All right, or does our group level have an effect on our measurement variable? Our null hypothesis is that the means are equal. Our alternate is that at least one mean is different. Our test statistic that we will use is the F. Degrees of freedom, none. And why not? We don't have to use the test statistic, but we are. It makes it easier to run it like an ANOVA. So I'll say, we can do like a randomized t-test. Our test statistic is a t, but we could also use the difference of the means as a test statistic and arrive at the same answer. So here we use the F statistic. Why is degrees of freedom none?
Because it's a random test.
And it's a randomized test, and we'll generate our own F distribution. And I will put F distribution in parentheses because it doesn't need to follow an F distribution. It doesn't need to follow the actual F distribution. We're going to use F as our test statistic, but we will generate our own distribution of this using the data. Will it follow the F distribution? Well, if all of our assumptions are met, then yes, it will. But if we violate our assumptions, then this distribution probably won't follow the actual F distribution. So, if all assumptions are met, if all assumptions of ANOVA are met, then our F distribution will follow the df1, df2 distribution. If the assumptions of ANOVA are not met, then our F distribution will not follow the df1, df2 distribution. And you could be asking, well, where is this F df1, df2? That is what we reported when we ran an ANOVA. We report our test statistic, we report our degrees of freedom, so that somebody can go look at that null distribution, see what the F distribution actually looks like, and confirm that your test statistic will generate the p-value that you report. But if we don't follow those assumptions, then we don't follow this distribution. And if we don't follow this distribution, then our p-values are going to be wrong. So that's the beauty of the randomization test. We don't make any of those assumptions. We're going to generate our own F distribution. We will generate our own p-value. All right, so test statistic, degrees of freedom, reporting. We will report our Conclusion, interpretation. We will report the test. The number of iterations, that's something new. And p-value. We normally don't report the test statistic in this case. We could, if we wanted to. So I could report the F. The R code. We will use a script. All right. Go back to here. All right. I am going to copy this script. Find it. Permutational ANOVA. Copy it. Paste it. And move over to Blackboard. I have now released 2 more R files. Permutational ANOVA and pairwise permutational t-test. So if I open up this permutational ANOVA, it's open. Here it is. Here it is. So it opens up, it's just a regular text document. You could open up in Notepad or WordPad if you want. All right, you could open it up in Word, but this is our function that we're going to use. It's not really a function, it's a script. All right, and what I've done was copied copied and pasted this part into this chunk. Oops. Let's fix this. Fix that. That's better. So this will not run. If you try to run it, it'll complain. You can't find stuff. No big surprise. That over. Save them. Save these scripts. So we are putting our dependent variable here. That's our measurement variable, and you're going to use the data $ variable notation for that. You're going to give the independent variable here. So that's your grouping variable, and again, use your data $ variable notation. And then you're going to put the number of iterations here. All right? And that's it. It's just these 3 lines. It's you replace this, you replace this, and you replace this. Those are the 3 things that you change. Leave everything exactly the same. And then it'll do everything for you. This code works as follows. All right. So first off, what it's going to do is generate or create a new x and y vector. All right. Do we have to do that? No, we don't. But this makes it easy. So you have one script, copy, paste it anytime you need to use it. All right. I think this is easier, copying and pasting this, than copying code that we're going to generate for our turkey example. Actually, probably the flower example. I'll leave the turkey as a practice. But it's easier to use the flower example and then try to figure out, well, what do I have to change in here? I can't remember. Here it is. It's already marked. Change these 3 lines. So we're going to create a new x and y vector. Then what we're going to do is specify the number of iterations. Usually, we're going to run 10,000. 10,000 seems to be an appropriate number. It's large enough to where we generate a sufficiently large sample or data set for our null distribution. Normally for what we work with, 10,000 will be sufficient. If you have an incredibly large data set to begin with, we may have to increase it up to 100,000, maybe even 1,000,000, and in which case you basically hit go and then you leave for the day and come back. All right, you let it run. But normally for everyday stuff, 10,000 is gonna work. Specified. All right, so we have that. Next up, next thing that it does is it creates the linear model and extracts, saves the F statistic. And this is F observed. All right, so in our code we have a linear model, and now you can see our substitutions. So we save depth var. That's our dependent variable. And we're making a linear model as a function of our independent variable, indivar. All right, so this is the generic aspect of it. It's going to work with anything as long as we change these two lines appropriately. And then what we do is we generate our ANOVA table and pull out the F value, which is how we do it, and save it as F observed. This is our test statistic. We're going to use this to calculate a p-value. And then the next thing that we're going to do is create an empty vector to hold our null distribution, which is f rand. That's what that will be. So f rand is our null distribution. And then step 5 is our loop. We're going to generate our null distribution. All right. So this is the for I in 1, 2 iter. This is saying for I, starting at our counter I. I is going to be our counter. We're going to start at 1, and then we're going to go up to however many iterations we do. So every time we get to the end of the loop and start back over, this I is going to increment. So it's going to keep track. And this loop now is going to generate our null distribution. How is it going to generate it? So the first step it's going to do is going to shuffle the independent variable. And this is sample without replacement. So we already have our group labels. Those are what we collected. What we're going to do is shuffle that up, because if our null hypothesis is true, that the means are equal, then they all came from the same group, they all came from the same population, and that grouping label is just arbitrary. And that's what we're doing. So when we shuffle, that our grouping label is random, or more specifically, that all data came from the same population. So shuffling is sampling without replacement. So the easiest thing, you have a deck of cards, 52 cards, all right? If we were sampling with replacement, we draw a card, we record it, we put it back. We draw a card, record it, put it back. It's likely that we're going to have duplicates or triplicates in our sample if we sample with replacement. That's the idea behind our bootstrapping. But when we sample without replacement, once we draw a card, we put it off to the side. We can't draw it again. So it's the same thing as shuffling, dealing out all the cards all at once, recording the order, then we shuffle it back up, deal it out over and over again. So what we're doing is we're shuffling to create our new category, And that ensures that all data come from the same population. This is our null hypothesis is true. That's what our null distribution is. If our null hypothesis is true, then this is what we expect of our test statistic. Once we do that, then we generate a new model, a new linear model using the randomized data, extract save the F statistic in the null distribution vector. Move this down. All right, so we shuffle our grouping variable. That ensures that our null hypothesis is true. Then we're going to fit our data to that randomized vector, that newly shuffled vector, and calculate an F statistic. This is this ANOVA of our LM, so you should recognize it. We've already done that, LM, but now instead of end of R, we're using R for our randomized vector. All right, we create our model. Instead of creating like mod 2 and passing that to ANOVA, we're going to do it all in one step. ANOVA, that's our F value. You see it up here as well. We're going to save it in F rand. That's our null distribution. Now I have the subscript because what we're going to do is this subscript specifies the row. So in the first row, when I is 1, this is our first time through, we're going to have our first F statistic, randomized F statistic. Then on the second loop, this increments to 2. So then we'll have the second row, and then the third row, and the fourth row. Over and over and over again until we generate 10,000 values. So the rest of our loop then is repeat A and B until we have n iterations. And that's our loop. So we're going to just repeat this over and over and over again until we have 10,000 F statistics in that F rand vector. Once we have that, we will then calculate the p-value. The p-value is the number, or is the proportion of values in F rand that equal or exceed F observed. So we're going to calculate our p-value. Not only calculate it, but report it. So this p-value is the proportion of F values in F rand that equal or exceed F observed. Note, F observed is one value that is in F rand, so we add 1 to the number of iterations that we have. So we actually observed it. When you get to, let's say, a sample size of 100 or sample size of 200, I think 100 is sufficient. The number of possibilities, the number of combinations that we could generate, random combinations, will far exceed that 10,000 limit. So there's a chance that in our F distribution, our F rand, we won't get F observed. All right, it's just not one of the options that we get. So what we do is, but we did see it. We observed it. We collected data. So what we do is we add that to our number of iterations. So for us, if we do 10,000, we'll have 10,001. This is partly why some people do their iterations at like 9,999, because it makes the proportions really easy. This number would be out of 10,000 at that point. So then you could just do however many values equal or exceed F observed and divide it by 10,000, real simple math. I like doing 10,000 because I think it looks a little bit better in a paper to say we did 10,000 iterations then. We did 9,999. I don't know, personal preference. Personal preference. All right. So we're going to get it. All right, so we added that note. Note 2. The smallest p-value possible is 1 over the number of iterations plus 1. The smallest p-value that we can possibly get is 1 over the number of iterations plus 1. Because that means we have one value, which is our f observed. There's our plus 1 for the f observed, over the number of iterations plus 1. So basically, the only value that equal or exceeded our f observed value is the one that we actually collected with our data. All right, so don't panic if I always get the same value. Yeah, this is why. All right, so let's work through this. So what we're going to do is use the example data set. What were we working on? Flower. Yep, flowers. Flowers.csv. Right? Returning to the flowers data set. I think it should be loaded. It is. Why it's not in here, beyond me. Save. Color and survive. All right. Returning to the flower dataset. We are interested in if in survival across the different colored flowers. All right, that's what we're interested in. And we know we violated the assumption, right? We violated normality. So let's run a permutational ANOVA to see if our results agree with regular ANOVA. In theory, ANOVA is robust to violation. So what we find from a regular ANOVA should match what permutational ANOVA. All right. So we're not going to check assumptions. We've already done this earlier in this markdown document. So let's run our permutational ANOVA. All right, so let's run our permutational ANOVA. I'm going to go back up, grab my script that I copied. Back over here. Paste it down here. And we have 3 lines to do. So our dependent variable, we have to use the data $sign variable. What's our dependent variable? Yep. It's our dependent variable. What's our independent variable? All right. You only have 2 variables, so survive and color. And then I would always suggest starting at like 100 to run it just to see if it runs. 100 should work with a snap of the fingers. If it works, snap of the fingers, then bump it up to 10,000 and run it again. Because what we don't want to do is have a mistake in our code where it's like a never-ending loop and it just sits there and runs and runs and runs and runs and runs, and you're like, well, is this ever going to end? So you can see right now at 10,000, mine's running, and I've got the stop sign, or the stop button that was there. Yours may have a stop sign. If you needed to stop it, you can, but just know you didn't run to completion. So mine ran under 10 seconds, which was a little bit of time, but it was sufficient. We ran 10,000 iterations, and I get this p-value. So, did you guys run it? What was your p-value? 0.018,798. All right.
0.19.
0.019.
Yeah, 1919.
Okay. 59.
0.017998.
Jeez. Okay. All right. I think we'll stop there. But hopefully you're getting the point that we're all reporting significant p-values, right? We're all reporting significant p-values. This isn't unusual. So smaller p-values. I'm going to run mine again. I'm going to write mine down and I'm going to run it again. So we can break it down to smaller p-values and larger p-values. All right. Smaller p-values tend to have a higher degree of precision. Or less variability. Larger p-values, less precision, more variability. And what that means is that when we have these small p-values, like it's 0.018, especially like anything less than 0.05 usually, if you repeat this over and over and over again, our values are going to be close. They're going to be pretty darn close. So there's not going to be an issue where, well, I ran it these 3 times, and then that one time that I ran it, I get a p-value greater than 0.05. It's just not going to happen. All right. If that happens, your p-values are jumping just madly, and it's probably because you have very small sample sizes. But once you start getting to p-values of, let's say, 0.2 and 0.3, and maybe even 0.5, now what you're going to see when you run it over and over again, your p-values are going to fluctuate more wildly. So let's say I ran it and it was 0.5. Maybe the next time I run it, it's going to be 0.6, and the next time I run it is 0.45. I'm varying over a much larger span, but it still doesn't change the conclusion that our means are equal. All right? So when you get small values, you don't really have to repeat this over and over and over again. You're going to probably see the same thing. Just likewise, if you get a large value, who cares? Your p-value is going to change. It's just going to change at a much larger scale, but still remain greater than 0.05. The concern is when we have close to 0.05. That's our concerns. When we have a p close to 0.05. Sometimes we get p less than 0.05. Sometimes we get p greater than 0.05. And now what we're talking about is going to give a range of, let's see, 0.048 to, actually we'll say 0.045 to 0.06, something like that. When you're in that range, then sometimes every time you run it, you could get a significant value, you could get a non-significant value. We're hovering right around that 0.05. If you get this, then come talk to me. In this class, we probably won't get that. At least when I create the data sets, I run them numerous times just to ensure that I don't see this. All right? But if you get this in a real life data, a real life situation, come talk to me. That's why I put it here. So that way we have it covered. If you ever have to go back to this RMD file to analyze data, you have it. All right? So we're different. Now what do we do? What's our next step?
Post-hoc test.
Post-hoc test. So what we'll do is we'll cover post-hoc test this afternoon. All right? And then we'll leave the turkeys example as like a practice problem that you can do as like homework, and we can go over it on Wednesday. And this is it. This is where we're ending. This is permutational ANOVA and then the post optimist. All right. And what you could, I didn't put the quiz. I'd say it's due on Wednesday,
Okay.
so it gives you time to do it this afternoon if you want to. Yep, I could give you this. We don't have a huge number. Here, Ryan. Josh. McGee. Good. So just a common one that was missed. Assumptions of ANOVA. Data are normally distributed within each group. I think that also popped up on the application part as well, where you did like a QQ plot of the dependent variable, and you see it not normality, but it's normality within each group. We have to do a QQ plot within each subset. So, all right, check it out. I have part 1 key posted outside my door, and then I'll have the second key posted. All right, see you at 2.